Yeah, okay. So I hope, so this is one small topic on basically medical image processing. So it's a general topic in deep learning, but during the past, I think at least few years, it has come to us as a great help in many practical situations. That's why I chose to do it. Okay. Now you are all familiar with some kind of deep learning, right? Yes, no, yes, yes. Okay, so you have all trained kind of some medical image classifiers, all those things. Anybody worked on semantic segmentation? No, not yet. Well, that's okay. We don't assume anything here. So, so the first thing we wanted to do is about this new paradigm called semi-supervised or weakly supervised learning. And then we try to see its application for the semantic segmentation task, which typically happens in many biomedical imaging. Okay. So so first 30 minutes or so we will try to look at what is this new semi-supervised method, and then we will switch to how we apply that to a medical image segmentation. Okay. So we have all seen what is supervised learning. You have a data and you have the corresponding labels, and you try to train it with that labels. So you have for example tumor detection. You give a patch and try to identify it as whether it's a malignant or a benign part, or you give a microscope slide and see if there is a infection or not. Many such things, right? So that is supervised learning. Unsupervised learning is, so supervised learning is with a teacher. There is somebody who is telling you what is the expected outcome, what you are supposed to do. So this is the input and this is the corresponding output, and this is what you need. On the contrary, unsupervised learning is something where there is no target. You just keep on exploring lot of data and try to come up with something which is either a data abstraction or a data clustering or many different things. So that's unsupervised learning. So this semi-supervised is kind of something in between. So supervised methods, I think it is pretty clear. You have some image and you have to figure out what the image is. So you give this image, it should say it's a rocket. You give this, it should say a boat, and so on, right? So this is a vehicle, craft, something like that. So these are like different. So you will have this, what is called as the label for the image in the data. Now semi-supervised is where you get some supervision, and at times sometimes you are on your own, you don't know what it is. So this is when we work in medical domain. This happens generally with the medical data. So you have a lot of medical data, and often you don't have what is called as the labeling. So because how do you prepare a full data set? Let's say you are trying to get, so we were working on a problem which is called fundus images. So retinal images, you take it through a special camera, you can image your retina, and the idea, so many of you might have heard this, a diabetic retinopathy. So somebody has to label, sit and look at every image. There are like very fine details happening in there. So a doctor only will be able to label. I mean, we won't be able to label ourselves. So they will go and say, okay, this belongs to diabetic retinopathy of this particular grade, grade 1, grade 2, grade 3, etc. So this labeling require a lot of expertise. Or even if it's a cancerous tissue, you need to really go in detail, because different tissues look different, and the characteristics of malignancy can be different. You really have to have an expert doctor sitting in, looking every patch to identify which is a good, which is a malignant part and which is a benign part. So this labeling is costly, whereas acquiring the image is many times not that costly. Okay. So you typically, I mean, this is our experience also. We were approaching a pathologist for some of these cytology images, and what we found is that they can give us like lot of images, hundreds of images, and the point is we don't have labels for them. So that's the setting of semi-supervised learning. So the doctor will be able to sit with you and give you labels of 100 images or 200 images. Rest of the data is not labeled, right? So that is the setting of semi-supervised learning. You have medical image which is partially labeled. Now is the all other data is useful or not without label? Without label traditionally we can't train that. Okay, so that's the semi-supervised learning. Okay, this much is clear. So it's about doing that. We have some set of labeled images, some set of unlabeled images, and how do we use this unlabeled images in learning something useful. Okay, so there are few assumptions here. So, okay, let me tell you what this picture means. This is just trying to separate two classes. So these are the orange class and the blue class. Now I don't have all these points in the training data. This is actually all the possible images, let us say, but I have only very few data which is labeled. So this 3 triangles is what I have labeled from the actual orange class, and this 2 samples from the blue class is labeled. So if I were to train a conventional supervised thing, it will try to look only at this 3 and this 2, and it will try to somehow draw a line between them which is separating those 2. Correct, no? Now of course that's one way of doing it, but then I also have all these in between points. Of course I don't know its color, but I also have all these points. Now SSL tried to assume a certain things about the data to come up with a better separation between those 2. So this entire thing is training data, but I only have labels for this 2. So what are the assumptions? The assumption is that the data is having a smooth distribution, which generally means the following. If you have a point here, the point which is very next to it will most likely have the same label. So if I have an orange point which is this triangle, these immediate next things will have the same orange color. That's one assumption. Then the other assumption is you have a plus which is blue color here. The immediate things will have blue color. Okay, so that's about this first assumption. Then it's about a low density decision boundary. The decision boundary won't pass through too many points. It won't cut too many points. It is supposed to be passing through a low density region. It will cut minimum number of points. And then there is a third thing which is called manifold assumption, which is illustrated here. If you think all these are becoming part of an arc, most of the class which correspond to that particular class will be same kind of the manifold. So that's a more technical assumption. We don't really do too much about this. Let's mostly concentrate on this. Okay. Now based on this, again we don't know how to train our neural network to do this, but we discuss a couple of methods in putting these things into action. Okay, so that's our agenda. There are like too many ways to do it. We will only discuss 3 or 4 things. Okay, so how do we do smoothness assumption? So those are the 2 things we said we will do: smoothness assumption and low density assumption. Okay, so how do we do SSL in practice? Okay, so this is from the standpoint of a neural network now. Okay, so how do we incorporate smoothness assumption? You have a lot of points. Now the smoothness assumption says that the neighboring points will belong to the same class. Okay, so what you do, you try to sample neighboring points. You have a data and you try to predict its output, and you generate a point which is its neighbor. How do you generate a point which is its neighbor? You just add some noise to it, very small amount of noise. You have an image, you add a little bit small noise to it, it is a neighboring point. And you predict that output. Those two outputs should be exactly the same. Do we get the point? So if it's a neural network, it's a neural network and those two outputs should be the same. So how do we make it same? We define some loss function and try to minimize that particular loss function. Is that okay? Now the low density boundaries, that's also in a similar method. So small changes in the boundary should not matter. You have a boundary, and even if you change the boundary a little bit, it should give you the same classification result. How do we ensure that? You have the model, you kind of look at the neighboring models. What is a neighboring model? The model, either you put a little bit drops few things, or you change the weights a little bit. So there are many ways of sampling these models. So you try to push the model little bit that side, this side, the model should still give you the same exact result. So those are two things which we generally do in SSL. Okay, so I'll give you a couple of examples and then we will go into the applications of the thing. Okay, so let me look at this. These are the probably most earliest attempts to do this. So this is there are two models which was proposed, which is called as the pi model and the temporal ensembling. So the pi model is what we said as the perturbing the data. You have a point and you try to push the point. The data you push it this side, that side, it should give you the same output. Okay. So this is actually the pi model. So you get a label and you get a image. Generally, if those two are there, you just pass through the model and you can train with a cross entropy. You update the weights with a cross entropy. This is the labeled data. Now you have unlabeled data which you don't know what is the label. So you cannot train it with a cross entropy. What you do is you take the image, you try to make different augmentations. You take let's say you add a little bit of noise, or you try to shift it slightly, 5 pixels you shift, or you rotate it by 4 degrees, or such things. I mean, these are called augmentations, right? We use it when we train to make the network robust. So you apply those randomly some augmentations and generate two outputs. One is the image as such and one is the image which is augmented. So you get two outputs, and according to our smoothness assumption, those two outputs should be the same. It should be the same. So you try to minimize the square distance between the two outputs. You have like 0 ones as a vector coming in the output. So you train it with the mean square loss, and your total loss is going to be the some kind of weighted sum between those two. So this is the pi model. This is actually perturbing the data to make a robust model. So you use labeled data for doing this and unlabeled data for doing this. Okay. A temporal ensembling is again with some the other thing where you actually try to look at different models. Okay. Now we don't, in this, at least in this example, you don't actually take the model and add noise to it. What you do is you are training, right? You have every iteration you are updating the weights. So you take the past 4 or 5 different weights which you have while training. So I have the whole data. I put one batch of data, I update the weight. I put the second batch of data, I update the weight. Third batch. So you are getting sequentially all these models which are only differing by a little bit small update in the gradient descent. So you take all those 5 models and you try to find one of the what is called as a pseudo label. You you have a model, you have passed 4 models, you give the current batch, you predict it using the previous model, you will get a previous prediction, previous prediction, like that you get 4 or 5 predictions. You average all the 5 predictions, you get a value, and that you treat it as your label, okay, so that's your label, and then each of these prediction of all the models, it should be same as that, because the model only changed a little bit because you only had 3 or 4 batches. So all these should be same. So you train it with again the mean square error between those 2 outputs. Those 2 outputs should be the same. You update the derivative and train it. Okay. I'll probably cover this. So the problem with this moving average of this model, sir, you need to keep a lot of models in the memory and keep on averaging those outputs, etc. So this is a slightly improved version of that. There are 2 different networks. One is called as a student model and one is called as a teacher model. So what you do is, okay, of course, if you have labels, you just try to do cross entropy training. But if you don't have labels, what you do is, so you keep another model which is averaged over the past 3 or 4 models. So you predict from both of them and try to see if their output is the same. So you try to do that thing. So that is typically the mean square error. All this consistency cost is what is actually the mean square error. Okay. Yeah, I'll probably skip 1 or 2. This is another thing. This is a virtual adversarial training. So what you do is, I said you perturb the data with some random noise. Now, you don't try to perturb it with random noise, you try to perturb it with a very adversarial noise. Okay, what is adversarial noise? So your noise can be anything. Let's say I have this vector. So input is a vector, right? I mean, you have a vector with some numbers as the features. Now you can add noise to anything. Let's say I'm adding a 0.021 to here, another 0.021 to here, let's say 0.003 to here. I mean, there are many ways to add random noise here. Now what is adversarial noise? Adversarial noise is, so this is just another vector, right? Another vector of very small values. Now this noise, when is it adversarial? It is adversarial when this is such that with a very small value of the noise itself, the output flips, and that happens in neural network. Okay, neural networks are very sensitive to this kind of very particular directions of noise. So that's known as the adversarial noise. So how do you find it? Once you have a neural network, you can try to see the derivative of the output with respect to all these input values, and you can see where that derivative is maximum. That particular vector is the adversarial noise. So you try to train it, perturb it with adversarial noise, not just any noise, and then you need to train with the unlabeled data where those 2 outputs are same. The input, when you get one output, the input perturbed with the adversarial noise, you get another output. So these 2 outputs needs to be same, and you try to minimize the mean square error there. So that's virtual adversarial training. I'll skip this, and there are 2 methods which I wanted to discuss. These 2 are the ones which we used. Therefore, both of these are from Google actually. They did it around 5-6 years back. This one and the next one also very close to it. So here, what they do is they do what is called as a mix match. What you do? You generate these pseudo labels from many augmentations. So you have one input that you need to actually get the, you need to train with this unlabeled input. I don't know whether this is car or bus or anything. So you get this input, you try to make a lot of augmentations. One is the car here, one is its flipped version, maybe a rotated version, everything. So you get some prediction, some probability at the output. And you kind of average all those probabilities and try to do something like a softmax. So your maximum will get pushed up and then all the other things will go down. And you take this and try to do a mean square error between this and these individual outputs. Okay, so you do a lot of them in one go. So it's a k different augmentation. So that is what is there called as a mix match. Okay. Now there is a fixed match also. It's again this is the next year after they proposed to mix match. They try to change something and try to look at these things. So you have again a data which is not having a label. You try to do a weakly augmentation, you get some output, and you do a strong augmentation and get output, and these two outputs should be the same. Here you do a sharpening, you do a softmax kind of transform. So you need this to be very much same. These two things should be the same. So this is typically a mean square error between those two outputs. So the weak augmentations are just flipping or shifting, which doesn't affect the image too much. And the strong augmentation is you shear it, you do a color transform, you add a lot of noise, all these things. So this is what fixed match does. Okay. Okay. So generally we were telling we have the option of perturb the model or perturb the data. I think perturb the data we saw mix match and fixed match. That is the final two things we saw. And we saw this pi model and mean teacher when we have the perturbation of the model. So that's the idea of semi-supervised learning. Okay, I'll quickly go through what is semantic segmentation. Some of you might know already, but because if anybody is there who doesn't know what is semantic segmentation, this is useful. So what is semantic segmentation? It is about, earlier you had only one object in the image. Now you have many objects and you need to label each object and find out where it is. So for example, this is a traffic scene. You need to figure out that this is a car, that's a road, and this is some trees, this is the sky, and I mean you get the idea. This is the building, and so on and so forth. So you need to label each and every point in the image. So you need to have class labels for every point. Earlier you had only one class label. Now if you have a 100 cross 100 image, you will have 10,000 class labels for each pixel. So of course, I mean other than lot of other things, it is useful for medical images, telling which of these cells are actually malignant. That is what we were working on. Okay. Yeah. So how do you actually measure how good it is? So we measure using many different things. Okay. So precision is precision recall is standard detection kind of thing. I'll just tell what is precision. So you have a lot of area which is malignant, and sorry, yeah, that's recall. Let me tell you what is recall. Recall is basically, let's say you have this whole area which is malignant. Out of that, how much did you actually detect as actual malignant area? So that is recall. So you had so much initially and you took back as some of them, that is recall. Precision is the other way. You have detected let's say some 100 parts as the malignant part. Out of this 100, how much is actually malignant? That is your precision. And this is some kind of an average between the two. Okay, so we will only be concentrating on that. So how do we do this semantic segmentation? So generally we have convolutional layers, followed by fully connected layers. People know this, right? It's a convolutional neural network. So segmentation, one way is you take small patches and try to figure out what is there. So this is actually trying to detect the cat probability for smaller patches of this image, and you see it is roughly around here, and it doesn't help much. So what people have come up with is this deconvolutional layers. It's a layer which is kind of up convolution. So this is the general neural networks work like this. So you have a convolutional encoder kind of thing, and then there is a decoder which comes up here. So, and one of the things which is very famous is this unit, just the architecture. So this was originally introduced to actually segment some of these cell images from the microscope. So this is kind of the input, and this is the kind of label. So it's some particular cell which is segmented from the microscopic image. So there are of course much more bigger networks which is being proposed. I'll skip that anyway. So what did we work on? We were working on looking at identifying malignant clusters of these cells. So this is a cytology image. People have prepared that slide, and it is under microscope and trying to figure that out. So generally at full resolution things look like this, and it is easy to actually identify, okay, this is a malignant cell. So these are the corresponding labels. The red part is basically the malignant cell, and the blue part is basically benign cells, and then it's a background, and the green part is basically the cytoplasm of the cell. Okay, so this is what is expected. Okay, now this is we can still do it. I mean, you can have these images and try to label these things and try to actually come up with, try to train the neural network. But when we get to low resolution things, it was almost impossible to actually do this kind of labeling. Okay, and it was this was taking a lot of time. Well, even this took a lot of time, but this was almost next to impossible in doing this. Okay, now why do we need this low resolution labeling? Is because these scanners, the slide scanners, they are very slow typically. Now the idea is you do a scan at a low resolution, it is faster. So you try to figure out where is the malignant area and then try to get that area at a higher resolution. That was the motivation behind this work. So that people can confirm that in a high resolution. Lower resolution, you suspect some malignant areas and then come back and kind of verify it in the high resolution area. So this was the problem that we worked on. So we kind of collected lot of data at different resolutions, and it was around 400 cross 400 patches, and this was the higher 40x resolution. Slightly smaller resolution will look like this. This is very small resolution. So we tried to work with this 4x resolution and 400 cross 400 image patches. So of course labeling, as I told, is manually intensive, and we need to confirm this whole thing with the doctor. I mean, I cannot just say this is malignant. I mean, you see that this is actually benign and this is a malignant cluster. I mean, I don't know how to do it. But the point is, we can't get the doctor to sit with us for all those few thousand images. It's almost impossible. So we try to minimize the labeling and then try to learn from both the labeling and unlabeled data. Okay, so that is basically the idea of semi-supervised learning, as we discussed, right? So this is a few initial things. So you just train 10x data. So basically this, so I had 40x data labeled. This data is mostly unlabeled. So what we can do is, you can just blow this up to 10 times more and try to test it on a model which is trained on this. So that option is there. Okay, so it will give you some idea, but this is inherently having lot of more noise and significantly lower resolution. It won't be a perfect model. So that's what we did. So we tried to build a baseline by training on the 40x data and test on the 4x data. So we got to something like some 0.73 average F score. So you see that this is basically an average of precision and recall. It's around 0.85, and this we didn't care too much because it's anyway benign cells. We were like more worried about these things. So all hyperparameters, everything is tuned for getting this higher. So it was this. So we tried to do those two algorithms, mix match and fix match, as we discussed. So mix match, as you remember, it is about you try to do lot of augmentations. You have the unlabeled image and you do lot of augmentation, change the color, put a noise, shift, rotate, all those things. So you get different predictions and you average them to get a standard prediction which you consider as the pseudo label, and each of these predictions should be same as this by the semi-supervised learning principle. So you try to minimize that mean square error loss. So this is done with that 40x data which we never bothered to label, and with the 10x this is a 4x data which is unlabeled. And the 40x data which is labeled, you can train in the usual manner. You have the label, you have the prediction, you minimize the cross entropy. So please, we keep on doing that, and finally we have some weighting factor between them as the final loss. So the only thing is, so you need to actually worry about the labels. Okay, so if you actually have a label here and you do augmentation which is shifting the image, you need to actually shift the label also. So we cannot just average these labels to get to that standard label in the mix match. So what people do is, so what we did is we tried to kind of then, so this is a rotated thing, it will give you a rotated label. You have to do the reverse of it before doing all those averaging. So we tried to do all that. We tried to do reverse augmentation for the labels, then try to come up with align all of them and then centering all those things, and try to do pseudo labeling. So this needed a few more stuff. I mean, you see that we only consider the center part because when you shift and rotate, some of these things are giving very weird outputs. So we try to avoid that. Okay, so these are like, this is just original one, this is shifted one, this is zoomed and cropped part. So you have to reverse the augmentation. So this image is at a different zoom and crop compared to this. So you have to reverse it and align all of them and then average to get the pseudo label. We used all those different augmentations, flipping, zooming and cropping, and height and width shifting, all those with some statistical probability. So every image you take with this probability, you might flip or you might not flip, and similarly. So the training, you don't worry about that. I mean, this is the loss which is the standard cross entropy loss, and this is the loss which is telling those two augmented image and the averaged output should be the same. So again, it's a pixel wise loss because you have a lot of class labels for each pixel. So don't worry too much about that. Okay. So we tried with the different k values and see how we could improve that. So I think here we actually got, so there are different lambda values, these weighting factors. So basically we are trying to optimize for hyperparameters here. And we kind of got to that result. So we had this one shoot up by another 4%, here another 10%. So we kind of made these two models same. So finally, when we got an average value, we had at least a 4% improvement here and another 2% improvement there. So something got better. So this is some results. So if you see, this was the image, and Okay, have the ground truth here. So there is an image and there is a ground truth there. So here it was all benign, here it was all benign this part, but malignant here. This is benign, this is malignant. But if you look at this, this is actually making everything malignant, these two images. This was actually missing the malignant portion. So this is the mixed match, this is the mobile unit. It was kind of predicting everything as malignant. This was predicting everything as benign. But after you do this averaging, this has improved here. After doing the mixed match, this also has started getting some of the malignancy. Oops. Yeah. So the other thing that we did was the fixed match. The fixed match was basically trying to look at another method, right? So you do a weak augmentation versus strong augmentation. So you have a labeled image, it is the same path as a supervised training. You label the image, you predict it, you have the label, you do a cross entropy loss. So unlabeled image, you do weakly augmentation and strong augmentation. This is just either, I think we also shifted and rotated. Basically we didn't we didn't add noise, we didn't keep color transformations, etc. So these were the predictions. This was considered as the pseudo label, and these had other predictions. Okay, and you tried to do a loss there. Sorry, this is not a cross entropy loss, this is a mean square loss. Okay, sorry, it's cross entropy. Okay, I'll check this. I think this was mean square error losses. I've labeled it wrongly. So you have two images. So again we have to kind of reverse all the augmentations before getting into this loss computation. So this is weakly augmented picture and this is a strongly augmented picture, and you try to do this. Of course this is also this is only the fixed match part. You also train it with the supervised data. So this is the kind of augmentations. The normal augmentations, which is flipping and shifting, those are used in the weak augmentation. Change the contrast, change the color, all those zoom and crop, I mean changing the scale here. So this is the range where we change the scale with that probability. So those are all used as the strong augmentation. So this too has to be have this. There will be two outputs from those two, and then we tried to do the loss. Okay. Now there was one extra thing which we did. That is, when the output, you get some probabilities, right? When you give the output, so you get a value saying that whether it is malignant or benign. Only if that probability is high, you try to include it in the training. So you don't include all the regions which are giving you low probabilities from the weak augmentation. So that's an extra thing we had to do, because otherwise it was not converging. So that's one thing we did extra other than the basic paper. Okay, so this is just a formula. So you try to have two different losses. One is supervised, which is standard cross entropy, and then the unsupervised, which is the mean square error. Here I put correctly. And you try to average. Again you try to look at various factors, various kind of weighting. So your unsupervised is kind of 10% weighed as compared to your supervised loss. So you see that it is actually still giving more weightage to the supervised term, but this, with a lot of data, this is able to improve this. So this is the kind of improvements we were seeing. So you had these two baseline models, which is if you only train with supervised data, their performance was less, and here this has improved. If you remember, this was something like 87 before, so this has become 89. This was smaller, and this has become 7% more to become 91, and Benenef score was even that actually improved. So both of these models came up to almost 4 to 5%. This has become 8% better, this has become 4% better. This was originally a better model than that, because this is having all those residual blocks, which actually is a better model. This gets trained better than that. Okay, so both of these base models, we were able to improve the average F-score, average precision and recall for these tasks. So again, similar set of results. So this is the baseline results. Baseline results are same. Mobile unit was predicting too many malignant regions, and REST unit was missing too many malignant regions. But with the fixed match, they were actually getting closer to the ground truth. So here this is, for example, still a misclassification, this region. But between these two, I think it is trying to get close to the ground truth. So that's the fixed match results. So I think this is probably the more important slide. The data is valuable. Whether you have label or not, try to get as much as data as possible. Okay, you may be able to get only few data points labeled, and many times it is not possible to label everything. But still you keep the data. And how do we do SSL? We saw at least 3-4 methods, and depending on your domain you can choose. If you think it's easy to do adversarial training, do adversarial training. If you don't have so much of computation time to generate all adversarial noise, etc., don't worry about it. But at least try to do a mean teacher model, or the other data augmentation techniques. Fixed match, mixed match, we found them to be pretty much working at least 2-3 different applications. And one of the crucial thing is here, so you need to have kind of comparable amount of supervised data also. So you should have at least, if you have at least 20% of the data, you should have supervised data. That's the kind of paradigm where it starts working. I mean, if you have like only 1% of data supervised and 99% of data unsupervised, you may not see that much of a performance improvement. Again, you will see that while we trained the loss function, it actually unsupervised loss function got kind of 10% weightage as compared to the supervised thing. So supervised data is important in this framework, but you can still benefit from a lot of unlabeled data. So that's the general idea. Okay. First one now. Any questions? Yeah.
So, sir, I actually appreciate the kind of work that you do, but I was kind of going through your Google Scholar profile. I couldn't find, there's one actually.
This one?
I couldn't get the page number also of the slide. I should have pointed you towards that.
We can go back and see.
Where you authored the paper with someone else, I think 2020 paper, please go back to the...
Yeah, I can tell you the paper, and yeah, I didn't put it here, yeah, sorry.
I saw it actually, but it's not on your Google Scholar profile.
Well, it is in my Google Scholar profile, but try to sort it by year and see if it is around, this was 2021, yeah, somewhere around that.
Maybe I skip that. So yeah. How about like, because I kind of tried investigating this, but what it gave me was not at all closer to it. I used the adversarial approach, okay, and it was one of the objectives I framed.
So you actually tried doing
on chest X-ray.
X-ray images?
Yeah, chest X-ray.
Chest X-ray, but this is a classification problem, right?
Yes, yes. So
and did you have label data?
So I had quite a few, but
how much?
It was around 300.
300 labels, okay, and unlabeled data?
Yeah, unlabeled is almost 15K.
Okay. And then, okay.
Yes, so
Okay, it's probably, how good is the supervised data?
so that's what, like, if you have your code, maybe I can look at that and see if I can adapt it.
I'll connect you with somebody. Yeah. Just send me an email. My email should be there, yeah, in the website. Yeah. Okay. Yes, sir.
I have a basic lack of understanding of the deep learning models for general image analysis.
Okay.
For example, in cytology, you train the classifier with cytology examples.
Yes.
And for breast cancer, with those examples,
Yes, sir.
domain specific.
Domain specific.
When you
Yes.
show a video and the cat and so on, in the general scenario outdoors, there could be many possible.
Yeah.
So
Okay.
you have to train with every
No.
habitat. You
So this one,
train only for habitat or what?
this is only trained with cytology images, whatever we did. Yeah. Only with the cytology images. Okay.
And habitat is trained only for cat.
No, this is actually trained with, so this is a general vision problem which is famous these days, image classification. So they do what is called as the ImageNet data set. There are around 1,000 different classes of images, and it's a 1 million image data set. And
1,000 types of objects.
1,000 types of objects and 1 million images, close to, I think slightly.
Open list. Right? It could
It's,
be anything.
yeah, it can be different things, yeah. So that, okay, I have lot of different data sets in these examples probably. Yeah, this is from the ImageNet classification. There are like lot of different classes. And this is one of the model for that. So you get 1,000 different probability values. And the point is, yeah.
1,000 networks, one for each.
No. Single network which has 1,000 output values. So the point is, this kind of part is kind of very general, because it can distinguish 1,000 different objects. Maybe it can different even other ones also. It kind of extract a relevant feature. So this is one of the model. Then this is another data set. I think it's a data set for, I think it's called Coco or something, MS Coco. This is for a driving data set. So they have a few tens of thousands of, these are actually, there are also another similar data set with videos. So they actually have these pixel level labels for, I think, a few classes which are generally on the road, like buildings, pedestrians, and obstructions, and road, tree, sky, etc.
And what happens when an unknown object comes?
It has to go as an obstruction or something. I think. Obstruction, say a road obstruction or something. I think, of course, it's a data set. It's limited always. What happens with the unknown object, it's still, I mean, we will have to look at it. So this is another data set, and these two are like I took it from outside. And this is, even this is another data set. It was coming in this challenge in ISBI. So it's a ISBI challenge, and it was around 2014-15, around that time. And this is from Google, and they tried to do some other thing. And this is our data set we collected from doctors.
So essentially the network has to be trained for every kind of object that you want to detect and label.
Yes. I mean even traditionally I think we will have, yeah.
That's a requirement.
Yeah. If we had, I mean even past, right? If you had to train a SCM, we had to train it on AMRI image. People are trying to do something across, but I don't know yet how successful they are. They tried to spool a few things like that ImageNet, that big data set I was showing, that initial part of that is kind of extracting general features. So they try to take those weights and try to add with other tasks, but it's only like it's a better initialization. It won't work out of the box, I don't think. Yeah, we
Just want to observe a labeling problem per se. We have a batch per se.
yeah.
in that patch, maybe 75% is cat is there. 25% is dog is also there.
So that is this task, no? Semantic segmentation. You kind of label this portion as same problem, right? I mean,
Is cat or a dog?
yeah, that's exactly where you have semantic segmentation. I mean, this whole image, is it malignant or benign? We don't know. But this part is definitely malignant cells and this part is definitely benign cells. It's the same thing. And that's where you need semantic segmentation, right?
Second observation is compared to supervised, when you compare supervised and unsupervised, supervised is fantastic like.
Yeah, but you don't get to data. You don't get to label. I mean, think about your satellite images. You get the satellite images of...
Unsupervised, we have not yet reached our expectation like as far as the models are concerned.
Yes. But that's... Yeah, but that's why it is important to look at more things on this, right? I mean, if you are looking at satellite data, it's very difficult to get labeled satellite data. You only have, I don't know, the Italian or US some data, and we have this entire India data which is available but no labels. And yeah, then I think you might know better, probably something in satellite data you have been working.
There's something that I really need to get clear. See, you said about semantic segmentation, right? But can you go to the previous slide?
Previous slide.
There was a place where we had multiple classes, right?
This is multiple classes,
Okay,
right?
so how about instance-based segmentation then? Because see, my understanding is semantic segmentation is we have a foreground and we have a background. Two classes.
Not necessary. It can be multiple classes, right? I mean, your driving problem, you have to identify vehicles separately, side separately. Yeah, it is a classification problem.
Yeah. So how do you implement instance-based, right? Then, like, if
How do you implement what?
instance-based segmentation? Like, see, in a class of car, so I have various models of car.
Okay, instance segmentation. Instance segmentation, okay, people do many things actually. One is, I mean, the simplest thing to do is a connected component analysis here, but not really always useful. I mean, it won't segment these two trees, right? So that instance segmentation is actually a bit tricky, okay, if you ask me. So there are models people propose for doing instance segmentation where you have to kind of have the object in different things and try to kind of get a 2D distribution of the object. I mean, you know that tree is like this. So you try to use that kind of knowledge to train segmentation of the whatever get classified as tree. I mean, you take all these yellow regions and then try to cut it into different trees. Yeah, so you have to train a separate model for that often. Anything more on instance segmentation?
So, like in pathology data, any image enhancement technique help to improve the performance?
Okay, yeah, that's a good question actually. So there are these two different schools of machine learning training. One is you get the data and you try to make the model robust to noise. So you get all the data, maybe good data, some of them bad data, but in spite of only using good data, you take the data, add some noise, distort it a little bit and train the system with all kind of inputs, whether it is good or bad. You try to train it with all kind of inputs so that the system is robust to these kind of distortions. So that's one way of doing it. The other way is, as you are telling, enhance the image and try to get it to a very good quality image and then classify. So they are both kind of approaches. So people these days try to do this, making the system more robust, because it's only just a machine learning system. They don't have to think what to do to enhance the signal. Often the enhancing the signal is a more difficult task. Sir, I think you should know. Yeah, you have to do all the signal processing and you have to learn all the distributions of the noise, everything. It's more difficult, but I think, yeah, if you can get to a very good SNR using your enhancement, maybe that's a good way, because your variability is reduced. You don't have noise in your data, so often you will be able to train a simpler machine learning system than very complicated. That's all.
Just a comment on what
Yes, I think, yeah,
It's an interesting observation. In textbooks, when we studied image processing, we studied filtering and enhancement as initial pre-processing steps, thinking that they're easy, and then classification is more difficult. Now you're telling me the reverse. That classification is easier than filtering?
No, it's not easier. Okay, sorry. The point is you need a much more, so you have this complexity of dealing it somewhere. So the point is you deal with some complexity in enhancement and lesser complexity in machine learning, versus you have a huge machine learning system and more complex machine learning system, let it handle everything there. So it's more complex. It's going to have more layers, more computation, more everything.
In addition, there could be noise in the label.
Yeah. That's also there. Yeah. So actually a very classical example for this is speech, because I have done some speech research, so I know this. So for at least 50 years, okay, people try to process speech in a particular way. They will take the speech, you know, I mean, you put a mic here and record, right? So you get a waveform, you get a very random kind of waveform. I mean, anybody have seen a speech waveform? It's pretty complicated, okay? There will be a ringing, and then there will be an envelope and all those things. So what people did to process speech is you take smaller intervals to this and try to get the spectrum of it, okay? Spectrum, you know, FFT, right? And then try to find that spectrum in certain bands which are important to hearing, okay? So lower frequencies are more important, so you take more lower spectral bands, and higher frequencies are not so important, so you take wider bands there. You put all these things and then you do a DCT. Don't even ask me why, but it's a way of smoothing out these fine variations in the spectrum, okay? And you get some random 20 numbers out of all this processing, and they seems to be very robust in doing this is called melt frequency Kepstral coefficients, if anybody wants to know. So they seems to be very robust to some of these variations, like I am speaking something, he is speaking something, his voice is totally different, all that signature is there in his speech. This seems to be robust against such variations. And even a different like a gender, I mean between male and female the speech changes a lot, right? So this seems to be very robust against those things. And people are only using this for like past, not past, I mean few years back, I think around 40 to 50 years people used this without changing. It was just exact the same signal processing which people did, and then this was fed to the machine learning model. Now with the deep learning, I think even us back as 2015, 10 years back, people have started to reinvestigate why we should do this. People started learning these filters as part of the network itself. So they put filters here, but the filter coefficients will be learned together with every classifier. But they also found that finally the filters learned are like similar to this, but not exactly these things. So there were the so that's another part. So in your neural network you can have very special layers. A convolutional layer is nothing but a filter. So you can have a filter which is processing the input, which can often learn from the data. So yeah, that's also there.
When you say that the machine learned filters that are similar to what were designed by human researchers earlier,
yeah.
It's a kind of confirmation.
Yeah, it's good to know.
By a machine later.
Yes, it's good to know, right? Yeah. Well, yeah, true. Sorry, then I can't hear you.
Dimensional feature that you extract, right?
The MFCC here.
Are equivalent to the features extracted by the CNS? That's what you're saying, right?
Yeah, okay. few details there. I mean, people are doing not exactly MFCC. There were like different things. Okay, there's a little bit history here. Okay, this MFCCs never worked with a neural network. Okay, that is because they have very different variance across different components. So what worked with neural networks were well filter banks. So it is filter bank, but at a MEL scale, at a smaller scale here and bigger scale here. So they tried to learn the filters. They tried to put a convolutional layer in the first few layers of the neural network and tried to tune their sender frequency and the bandwidth. So it turns out that this happens to have similar structure. They have more sender frequencies here and a smaller bandwidth here and their wider bandwidth. Okay, Raghavendra, I think I am running.